Are there any questions? All right. So the question I posed to you at the end of last class was, if I took a capacitor and then I attached two wires to it like this. First off, what's going to change by splitting the wire and connecting it in two spots?
Didn't you say the capacitor split too?
That's the next step.
That's the next one.
But just when I connected with two wires instead of one wire, does that change my capacitor at all?
I don't think so.
Doesn't seem like it would, but.
Now, if we look at our formula for capacitance, for a parallel plate capacitor, we got kappa epsilon naught A over D. None of that has changed. Now if I split the capacitor, let's think back to the more formal, or the always works definition. Are we losing any charge by cutting the two plates in half? Has my voltage changed?
No,
So I'm still holding just as much charge.
but there's less surface area.
Say it again?
But there's less area because the capacitance, the capacitors are now split.
Okay, so the overall charge has stayed the same. My voltage has stayed the same, but now I've got two smaller capacitors because, as Brooks said, the area's changing. My area gets cut in half. Well, D is the same, epsilon sub naught's the same. My dielectric hasn't changed. So if area gets cut in half, my capacitance gets cut in half. So we can generalize it that, let's say that this was a 6 farad capacitor. If I cut it directly in half, well, that becomes a 3 farad capacitor and a 3 farad capacitor. Suppose I cut it in uneven amounts. So there's my 6 farad capacitor and I split it there. If this is 4 farads, what is that one?
2.
So when you think about the current flowing, or the charges flowing, so I have these electrons that are coming up to this junction right here. So this is a junction. Junction is any point where there's a choice of one path or another. The electron can go to one plate or the other at this point, and whichever plate it goes to, it chases a positive away from it, from the other plates. But it connects up again. So if I think about current flowing, I have negative charges flowing this way, and then ignoring the gap, negative charges flowing this way. I think I misspoke earlier, it chases a negative charge off. If they split at one point and join back up, this is known as parallel. Parallel construction, I guess we could say. So this would be an example of capacitors in parallel. So for capacitors in parallel. The equivalent capacitance is just the sum of all the capacitors that you have in parallel. So if that's a 3 farad capacitor and a 2 farad capacitor, it's a 3 farad capacitor whether I have a battery hooked up to it or not. because capacitance doesn't actually require it to be hooked to a battery. If you wanted to actually still charge, it does, but. So if I have a 3 farad and a 2 farad capacitor, and I want to replace that with one capacitor, what would be the equivalent capacitance?
5 farads.
Yep. All right. Any questions on the parallel capacitors? All right, now over here. I have 2 plates here hooked up to a battery as usual. Some distance d between them. And then I decide to make the plates farther apart. Let's say that it is now, not drawn to scale, 3 times the original distance. What does that do to my capacitance?
Reduces it,
Okay, by,
factor of 3.
yeah. So if this is 6 farads, this becomes 2 farads. And now I take these 2 plates that are separated, so this plate right here is that one, and this plate right here is this one, and then I stick these, I basically stick 2 plates with a connection junction between them, or, I mean, physically that's the representation. It could just be this block of metal that I stick in between. But I have these 2 plates with a connection in between them, so that the distance between here and here is d, and distance between here and here is d.
Would the total then be 12 farads?
It would not. Wait, do I want to do it that way? In other words, getting towards there, something. I don't want to specify it that much. I'm going to keep it generalized for right now. We'll make it specific in a moment. What can you tell me about this capacitance versus this capacitance?
It's higher.
Yeah, because the distance between these plates is smaller. So, think about the charge that's being held here. What can you tell me about the charge on this plate versus the charge on this plate?
Are they the same?
It is the same. So, because once I have these things charged, just sticking a plate in between, so if I take this middle section here, and let's go for a different color just to make it stand out. And of course, the stunning visual effects. Yeah. So I take this, so I have my capacitor, my 2 farad capacitor, and I just stick this neutral thing in between. All these negative charges here are just going to chase negative charges off of this plate over to this plate. So if this is some charge Q here, sticking something in the middle is not going to change this charge, but it's just going to chase charges over here. And so this will become, I guess if that's negative Q, this is positive Q. That'll become negative Q, that'll become positive Q. So I'm storing the exact same amount of charge for the exact same amount of voltage. What I'm getting towards is these 2 capacitors here, when put in this situation like this, will create something that is smaller than either of them to start it with. This situation right here, if you think about, I have charges coming off the negative side of the battery here, coming up to this plate, and then sort of traveling all the way through. There's no junction there. There's no point where a charge is going to go, am I going to go left or right? This is known as series. So these are capacitors in series. let's actually do that derivation a little bit better than I did this one. So this small one here has some capacitance C1, this has some capacitance C2. Look into a battery of some voltage delta V. I know I'm going to gain voltage going across the battery when I go from the negative to positive terminal. I'm going all the way around. When I get back to where I started, I should have no potential difference. So I gain going across the battery, I'm going to lose going across the capacitors. Or think about it this way, I've got my negative side of my battery here on the right. It's going to put negative charges over here on the right plate, which will make the left plate on the second capacitor positive, which will make the right plate of the first capacitor negative, and the left plate positive. So if I gain by potential going across the battery from negative to positive, I'm now going to go across the capacitor from positive to negative, so I'm going to lose some more, and then I'm going to get back to where I started. So whatever I lose across C1 plus whatever I lose across C2 better be what I gain going across the battery. So the potential gain across the battery should, I guess, minus the potential gain, put PS for power supply, minus potential drop across C1 minus the potential drop across C2 is equal to 0. Well, I know that capacitance is the charge held divided by the potential. So my potential is just Q divided by C, assuming they're fully charged. So delta V, the power supply, minus Q over C1, Q1 over C1 minus Q2 over C2 is equal to 0. What I'm trying to do here is figure out if I need to replace these two capacitors, what is the capacitance I can replace it with? In other words, what is the equivalent capacitance of those two? So if I think about, I have the exact same battery there, except now I've hooked it to a single capacitor, which I'm going to label a CEQ for equivalent capacitance. What does this need to be in order to be able to hold the same charge? In essence, the voltage of the power supply will now be my drop across my equivalent capacitance, and so this becomes Q equivalent over C equivalent is equal to, add these to the other side, Q1 over C1 plus Q2 over C2. And as stated before, the charge is the same in every case. Whatever charge I have on capacitor 2 is the same charge I have on capacitor 1. And that's, in essence, it's the same charge I have on these outer plates here. So all my Q's are the same. And so I have 1 over the equivalent capacitance is 1 over C1 plus 1 over C2. And so for capacitors in series, 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus however many I have. Dramatic pause for questions. All right, so let's actually do something closer to reality here, or do something more concrete. Not need to be hooked up. So if I have a 4 farad and a 3 farad capacitor in series, again, series, whatever current is flowing does not have any other path to take. What is the equivalent capacitance? 1 over the equivalent capacitance is 1 over 4 plus 1 over 3, which is 7 over 12. And so the equivalent capacitance is equal to 12/7 farads. Now, why would you want to reduce capacitance? All of this stuff, when we're talking about capacitors and then we talk about resistors, it's all about trying to control current. Because electronic devices need current flowing through them, and they need a certain amount. Too much current, it'll burn out. Not enough current, it won't run. And so you have, within this course, only a couple of choices in order to manipulate the current flow. We'll have resistors, we'll have capacitors and batteries. That's basically this course. And just a hypothetical situation is you need a very specific capacitance, but you don't actually have the capacitor. Can you create it from what you have? Well, through parallel and series capacitors, maybe. Try something more complex. Make it 4 farads. Farads and 2 farads. What is the equivalent capacitance of this 3 capacitor system? And why don't you see if you can figure it out without my saying it first.
You have 20 over 9.
Don't forget actual assessment for the units.
Okay.
But yeah. Brooke, you have it?
I figured it out.
Why did you multiply?
That's just bad. Okay, never mind. It's good.
remember that we have rules for parallel and rules for series. So, the question is, do we have two that are in parallel or two that are in series? And that's what you would do first. Yep, you do that first. And then you create a series. Yeah, now you're on roll. You were treating them like they're all in series,
Oh,
but
okay.
those are
Just
parallel.
something, okay.
Let's take a look as a group. Again, as I said to Freddie, we have rules for parallel and rules for series. Series, the current comes in and there's no choice. If you think about current flowing all the way through, current has no place where it can turn off. Parallel, it splits and then joins back up again. Here, the 4 farad is not in series with this and it's not in series with that, because I have a junction in between. Series will not have a junction in between. These are in parallel though, because I have a junction with beginning and junction afterwards. Current would split and then join back up again. So I apply my rules of parallel here. So this becomes 1. I got my 4 farad capacitor there, and then my equivalent here, you just add them straight up, 5 farads. Now I have a series. And so 1 over my equivalent capacitance is 1 over 4 plus 1 over 5, which is 9/20.